we're going to show that the derivative of the inverse tan function is 1 over 1 plus x squared. All right, so let's see how to do this. So we start kind of similar to what we did for the inverse sine function. We're going to just rename this. We're going to call this y. So we're going to say, let y equal the inverse tan of x. So we're just kind of naming this thing. We're just calling it y. And then from here, we're going to use our definition of what it means to be an inverse function. Kind of use the cancellation property. So we're going to apply tangent to both sides of this equation. Just like we did for the inverse sine and when we were doing that. All right, so let's see what we get. So we have this equation here, y is equal to inverse tan of x. We're going to apply the tan function to both sides. So we're going to get tan of y on the one side. So we're going to get tangent of y on one side. And then what happens on the other side here, we're going to have tangent of the inverse tangent of x. And what happens when we have a function and its inverse function right next to each other like this in a composition? They cancel out. And so this is just equal to x. So we're just kind of using the cancel property here. Tan and its inverse tan and the inverse tan cancel out, and we're left with just x. So when we apply the tangent function to both sides here, we get tangent y on one side, and then we get tan of inverse tan of x on the other side, but those just cancel and we're left with just an x. So we'll write it as x equal to tangent y. And that's just the definition of what it means to be the inverse tan function. All right, from here, then we want to actually do our implicit differentiation. So this is where our implicit differentiation takes place. Okay, so we just apply the derivative to both sides. So we're going to apply the derivative to the left side and then to the right side. And just like normal implicit differentiation, derivative of x, we differentiate that like usual, so we get 1. Differentiate the right side like usual, so we derivative of tan. We've proved what the derivative of tan is, secant squared. So we get secant squared of y. And we're differentiating a y term here. So we differentiate it like usual, but then we multiply by y prime. So we get secant squared y times y prime on the right. All right, so now this is pretty good, but we want to actually convert our y terms. So that's the next portion of this. We want to convert all y terms back to x. So we want to get rid of this secant squared of y and write it as some function involving just x's. The y prime is okay though. And how we're going to do this is, again, with a right triangle. So let's start with our right triangle here. So we have our angle, the opposite side, the hypotenuse, and the adjacent side. And our right angle is right here. Now, when we think of tangent of y, the tan function can be thought of as relating the adjacent side and the opposite side. So it's, what is it? It's tangent is sine over cosine. So this is opposite over adjacent. And then from here, we want to kind of look at what the pieces are for our tan function here. We want to relate it to what we actually know. Tan of y is equal to x. So if we can write that as x over 1. So we know tangent of y is equal to x. So that means tangent of y is equal to x over 1. And then we just kind of match up the fractions here. So the opposite side must have length x. The adjacent side must have length 1. And then to find the missing side, and this is our y right here, y is the angle. So then to find the missing side, we just use the Pythagorean theorem. So adjacent squared plus the opposite side squared is equal to the hypotenuse squared. And what we get then is the hypotenuse must be equal to square root of 1 plus x squared. Again, Pythagorean theorem, what was that? Adjacent squared plus opposite side squared is equal to the hypotenuse squared. So we know the adjacent and the opposite side from this formula right here. So we can find the missing side of our right triangle. Once we have that, then we're interested in knowing what secant y is. So secant y is, well, secant is 1 over cosine. And so the reciprocal of cosine, what did we had it before. We looked at cosine of y and we said it was the adjacent side over the hypotenuse. So this was in the last example. Cosine of y is the adjacent side of over the hypotenuse. So the reciprocal of that must be the hypotenuse over the adjacent side. And so we know what the hypotenuse is. It's the square root of 1 plus x squared. And we know what the adjacent side is. That's a 1 right there. So secant y, the hypotenuse is that square root term. The adjacent side is 1. So we know secant of y is this square root. So we can just fill that in. So we end up with the equation 1 is equal to square root of 1 plus x squared. And it was secant squared, so we're going to square this, times y prime. And then finally, the squared and the square root cancel, and we're left with just 1 plus x squared times y prime. And then finally, we want to solve for y prime. That's the kind of the last step here. Solve for y prime. And so if we do that, we want y prime by itself, so just divide both sides by 1 plus x squared. And we get y prime as 1 over 1 plus x squared. And we've just showed it. The derivative of inverse tan, we called inverse tan, we just renamed it y here. So the derivative of inverse tan is equal to 1 over 1 plus x squared. So we've actually proved it. And again, it's first using what it means to be an inverse trig function, or inverse function in general. Then we use our implicit differentiation, and then we have to convert back to a variable x, and then once we've done that, just solve for y prime. All right, so we'll try a few more examples like this coming up. Next, we're going to look at, though, the general exponential function.